Hello, everyone. My name is Roger Dev, and I head up the Machine Learning and Analytics group with HPCC Systems. I'm going to talk today about a couple of subjects. It's a double feature. First, we'll talk about the latest developments in our machine learning and analytics library. And then we'll look at a visual analysis of datasets using our new causality libraries. We have four new developments in our machine learning and analytics area. The first one is an accelerated Gaussian process regression. Second is mixed type data clustering. And then we have two versions of our causality toolkit that we'll be talking about. So Gaussian process regression is a nonlinear supervised learning technique that allows you to do regression on data of any form. And it doesn't require a lot of data to produce meaningful results. With just a few points, it starts to approximate the distribution that you're trying to model. And as you add points, it gets closer and closer to the actual distribution. It does have one minor problem, though. It doesn't scale well with large data sets due to the kernel implementation that underlies it. So we've addressed this by accelerating the kernel using random Fourier features. This is a fairly new technique developed by Al-Rahimi in 2007. And it's an award-winning technique that's proven itself very well in several applications. The approach is that you've got a kernel that you're trying to approximate, and you can approximate that by choosing randomly Fourier features. And those Fourier features, as you add them together, as you add more and more Fourier features, they'll approximate the kernel more and more precisely. So this allows you to control how much time you want to take versus accuracy. And it also provides much faster and more scalable results than you can get without this acceleration. Our second innovation is mixed type clustering. The clustering attempts to identify similar items within a data set. And it's an unsupervised learning technique. You can point it at the data set and it will automatically attempt to find the most meaningful clusters. We have a variety of techniques in our toolkit: k-means, k-modes, dbScan. dbScan is our flagship clustering algorithm. But they suffer from a problem. They don't deal well with mixed data types. And most real-world data sets have a mixture of data types. They have categorical data like gender and occupation. They have numeric data like age and weight. And generally, there's a mixture of those. So there are various approaches to blending the categorical and the numeric data within a single clustering approach. And my associate, Lily Xu, who also developed the Gaussian process regression, by the way, is working on this. She's currently researching and developing new methods for combining categorical and numerical data within a single clustering session. All right, now we're going to talk about our causality toolkits. Version 1 was released this spring. It's got Python underpinnings, and which are parallelized using ECL on the HPCC platform. These algorithms, as you might know, are very intensive, and we can accelerate them greatly. They're mostly fully parallelizable, and they run very quickly on HPCC clusters. The version 1 toolkit has 3 submodules: a synthetic data generation module. This allows complex multivariate, which means multivariable data sets, to be constructed that have intricate relationships between variables. And we can simulate real-world data sets this way. But the big difference is that we know what the causal relationships are, so that when we run our causality algorithms, we know when they're right. Running on real-world data sets, you don't know when you're right and when you're wrong because you're looking for answers. You don't know the answers. Secondly, it has a very powerful probability subsystem. We really consider our causality products to be general data analysis products. If you're trying to understand your data set, this is the system you're going to want to use. And finally, there are various causal analysis algorithms, and we'll talk about some of those as we go forward. Version 2 toolkit is currently under development, and we've begun testing it against real-world data. This brings up some new challenges, and we found areas where our theoretical approach did not work against real-world data, and we had to make some changes. It's got improved handling of categorical data. Now we can handle textual data directly without having to map it to numeric values first. And we can handle any combination of textual, discrete numeric, continuous numeric, and numeric categorical data, all transparently. We've added new state-of-the-art algorithms for conditional probability testing, independence testing, directional testing, and causal discovery. We're actually using machine learning within the causal algorithms now in order to perform the analytics. And a new visualization module that allows you to see graphically with 2-dimensional and 3-dimensional graphics exactly what's going on within your data set. And we'll be taking a look at this. We'll be looking at the results of the new algorithms and the new visualization bundle as kind of a preview. The full toolkit won't be available for a few more months. But we will give you a preview of that next. So we'll move on to the visual analysis of data sets using the HPCC Causality Toolkit. So we'll be using a Jupyter Notebook for the rest of this presentation to present the visualization capabilities. And we're going to be looking at 2 different types of data. First, we'll be looking at a synthetic data set with some reasonably simple relationships. And then we'll be looking at a complex real-world data set. So first, we'll look at a synthetic data set. And this is built using our synthetic data generation module, the Causality Toolkit. And the way that's done is just by building a structural equation model, a set of simple equations. They're statistical equations that determine the relationships between all the variables in the model. In this case, we've got a model with 4 x variables or independent variables that then have various nonlinear functions that relate them to 4 y variables. And in particular, x1 affects all 4 variables, x2 affects 2 through 4, x3 affects 3 and 4, and x4 only affects the 4th y variable. So we'll take a look at what that looks like visually. So we start out with a look at the x variables. So these are various distributions that were created by the synthetic data generation module to emulate things that can happen in the real world. X1, we see, has 2 humps. This is called a bimodal distribution, and it's usually an indication that there are multiple types of items mixed in the same basket. So if I was looking at the diameter of a basket of fruit consisting of oranges and plums, it may look something like this distribution. The second one is a trimodal distribution. It's got 3 peaks, and the same thing. This could be uh, oranges, plums, and kumquats. The third distribution is unimodal, but notice that it's chopped off at the ends. This is a truncated distribution, and most real-world distributions are truncated in one form or another. If you ask people how many children they have, very few people will give you a negative answer. So the distribution doesn't continue beyond 0. And it also probably doesn't go up to 20. The final distribution, X4, is a half normal distribution. And this is also very common for positive numbers. So this is what the basic data looks like. It doesn't tell you anything about the relationships yet, but you can see what the source data looks like. Now, as we add nonlinear relationships between those source variables and these target variables, the y variables, we see that they don't resemble the original distributions very much. We can kind of see a wannabe bimodality in this y1, because that's only dependent on x1. But as you add more variables, notice that they look more and more like a normal bell curve. And this is an illustration of the central limit theorem, which says that as you add various types of distributions together, they resemble more and more a normal distribution. So you can see that actually happening in the data here. And now we can take one of those distributions and blow it up and get more information. Here we show the mean, the standard deviation, the skew, and the kurtosis, which are the 4 major descriptive elements of a distribution. The green line represents the mean, so you can see that this distribution is skewed far to the right. The shaded dark blue areas or medium blue indicate 1 standard deviation from the mean, and the lighter blue show 2 standard deviations from the mean. So you can see the width of the distribution that way as well. Now let's take a look at another view. We have a facility called the heat map, and we can do 2 different types of heat maps. The first one is a correlation heat map. And this shows you which variables are correlated. So you can see if you look halfway down, y1 is correlated with, start from the top. x1 is correlated with y1, y2, y3, and y4. x2 is correlated with y3, 2, 3, and 4, but only mildly. x3 is correlated with 3 and 4, and x4 is only correlated with y4. So this shows you the relationships, and the deepness of the color shows how strong that relationship is. And the blue color indicates a positive correlation, and the brown color represents a negative correlation. So that's the correlation heat map. We can also look at a dependence heat map. Now the difference, we usually think of the difference between dependence and correlation is correlation is linear. If things can either correspond to higher values in the causal variable, can correspond to higher values in the effect variable, or it can be inverted, right? It can be a negative correlation, and higher values correspond to lower values. But with dependence, the values only go from 0 to 1. It's either dependent or it's not dependent. And the darkness tells you how certain that dependence is. So if we look, for example, at x1, we can see it has very certain dependence with all 4 of the variables. As we get down to x2, those dependencies become a little bit weaker, etc. But notice that all of the y variables are dependent on each other. So there's a dependence between all the y variables as well as between the x and the y variables. And that's because the y variables have x components in them. And specifically, y1 is in all four, x1 is in all four y variables. So now let's take a look at a different approach. Let's take a look at the joint distribution of two variables. Here we're looking at x1, which was the bimodal distribution, and x3, which was the truncated bell curve. And if you're looking at the joint distribution and you look from one end, here you see the projection of x3, the truncated bell curve. If we look at it from the other side, we get a picture of x1, the bimodal distribution. So that's an interesting aspect of joint distribution plots. The other important aspect is that if you look at it from the top, you notice that there's no diagonality here. You can see things happening from left to right. You can see things happening from top to bottom, but there's nothing happening on the diagonal. And that is a sure indication that these variables are independent. And in fact, these two x variables, x1 and 3, are independent of one another. We take a look at the joint distribution of, in this case, it's x1 versus y2. And again, if we look at it from the side, we can see y2. If we look at it from the other side, we can see x1. And if we look at it from the top, you'll notice that there's diagonality there. Things aren't directly aligned left and right, top to bottom. And that indicates that these variables are dependent. All right, so that was joint probabilities, and they're kind of useful, kind of interesting, but they don't directly tell you what's going on. Now we're going to look at conditional probabilities. And in this case, we're looking at the condition, the probability of y1 given x1. And recall that y1 is a function of x1. So from this angle, the graph doesn't look like much. But when we look at it from the top, it reveals the shape of a hyperbolic tangent. And the hyperbolic tangent was the nonlinearity that connected x1 and y1. So conditional probabilities reveal the function that exists between the source variable and the target variable. And the width of this tunnel describes the noise that's around that variable. So conditional probabilities are very revealing. This is another way to look at conditional probabilities on a two-dimensional graph. The blue line, the dark blue line, indicates the expected value or mean for any given value of x1. It shows you the expected value of y1 given x1. And again, you see the hyperbolic tangent shape clearly. The dark blue and light blue or gray areas around it show the standard deviations. That's the noise. That corresponds to the width of the tunnel in the three-dimensional graph. So again, the conditional probability highlights the function between the two variables. Now, here we're looking at y2 given x1. Recall that y2 is a function of x1 and x2, but still we see the hyperbolic tangent shape, the S curve. And it's a little bit attenuated, a little bit squashed. and the noise is much wider here. But we can still see the shape of x1 even when there are of the effect of x1, even when there are other variables in there. Similarly, if we look at the same y2, but we condition on an x2, now we can see the sine wave, which was the nonlinearity present in x2. And so again, we're exposing the relationship of the source variables to the destination variable. So let's take a look at a few more things here, and then we'll move to the live data. This is the conditional probability of independent variables. We look at this one from the side. We see our x2, which was that trimodal distribution, the 3 peaks. And we notice that no matter what the value of x1 is, it's got the same shape. Same shape throughout. So that's how you recognize when you're conditioning on a independent variable. So this is, we're looking here is x2 and x1, and we're looking at the conditional probability of them. And they're independent, so all you really see is x2. Doesn't matter what the value of x1 is. Similarly, we can look at the shape, the 3-dimensional shape of 2 conditional variables. So in this case, we're looking at the expected value of y2 given x1 and x2, which are the 2 components of that. And you can see in one direction, you can see the sine wave shape. And in the other direction, you can see the hyperbolic tangent shape, the S shape. And so sometimes looking at both shapes, both the 2 dependencies at the same time, gives you more insight, as we'll see when we go into the live data. All right. One more. Now we're going to look at things from a causal perspective. So we asked it to produce a causal model from the data and graph the results. And so here we're actually peeling back all the layers of interaction between the variables and trying to understand what causes what. And you can see x1 causes y1, y2, y3, and y4. x2 causes y2, 3, and 4, etc. So it reproduced the causal structure inherent in the data just by looking at the data. Now the lines, the deepness of color illustrates how strong that causal relationship is. And the color, whether it's brown or blue, tells you whether it is a positive relationship or a negative relationship. So x3, for example, suppresses y3 and y4. And the numbers there are the actual causal effects. Those are the strengths of the causal effect between these variables after peeling back all the layers of interaction around them. So this is with the synthetic data. And now we're going to move to some live data. And for live data, we're looking at a data set that comes from this CDC called the Behavioral Risk Factor Surveillance data set from year 2020. So they surveyed 400,000 or so people and asked them 279 questions about health and risk factors and demographic factors. And out of those 279 variables, we extracted 32 that we thought were interesting. We could have found a lot more interesting data. It's a very, very useful, interesting data set, but we wanted to keep it to a reasonable number. Just to illustrate the depth of multivariate relationships, there are 1.8 quadrillion different probability queries that we can issue against these 32 variables. So to understand the full interaction of the variables in this data set would take several lifetimes. But let's take a look at the general data. So here we have age, and the average age peaks somewhere around 65. Starts at about 18 and goes up to 80. Gender is close to 50-50, female, male. Notice that the Causality Toolkit can support textual data as well as numeric data. Height, this is a kind of a lumpy distribution. If you look at the top two peaks, there's a kind of a bimodality to it because it includes both males and females in the same basket. Weight is kind of surprising, how spiky it is. And this has to do with the fact that people generally estimate their weight into buckets. So I'm 180 pounds as opposed to I'm 183 pounds because your weight may vary from day to day. BMI, that's body mass index, is a very skewed distribution, as you can see. There's a question of, are you a veteran? And about 85% no and 15% yes. There's information about smoker types, never, former, everyday, or occasional, physical activity, income. Income happens to be bucketed into 7 categories. Education, from college to none. General health, from very good to poor. And the state of residence. You can't really see the states here because I've got a small graph, but we'll see that later, and we'll expand it in more detail. And this shows just the number of people that were surveyed in each state. All right, so we're going to look at the similar charts to that we looked at with the simulated data, but it'll be a little bit easier to understand the power with this live data. So, for example, if we start with the bottom line here, general health, we can see that it's negatively correlated with age. It's very slightly positively correlated with gender, which means that males report very slightly better health. It's correlated with height. That's interesting. It's negatively correlated with weight and BMI, as one might expect. Very slightly negatively correlated with being a veteran, negatively correlated with smoking, positively correlated with physical activity, income, and education. So this starts to give you an overview of any factor you want to explore. You can look at all of its interactions with other variables. You can now look at the same thing from a dependence perspective. One interesting thing to point out here is if we look at age and income, they're very, very lightly negatively correlated. But if we look at the dependence between them, we get 98%. And so they're fully dependent, though not very well correlated. What does that mean? Well, turns out that that means that your income goes up for a while as you become more experienced in your work, and then it goes down as you retire. And so the overall effect is very minimal, but it's very tightly dependent. All right, so now this is just an expansion with more variables. So I just wanted to point out, if we want to find out what diseases are correlated with age, well, depression is negatively correlated with age. You get less depressed as you get older. Kidney disease, cancers, skin cancer, diabetes, and COPD are positively correlated with age. And asthma is neutral to age, and arthritis is positively correlated. And the bad news for all of us, general health is negatively correlated with age. Our health gets worse as we age. Not surprising. All right, so we talked a little bit about this variable, income with age, and you can see that it goes up over time and then goes back down. There's very little correlation because of that, but definite dependence. Here we're looking at some health factors. This is the probability of health being good or better. So good, very good, or excellent, given your age. And again, no surprises. It gets worse as you get older. But good news is it's not that much worse. So it goes down from 95% reporting good health down to about 80% by the time you reach age 80. One slight surprise here is this little uh, rise around the age of 60 to 68. And we'll come back to that later. So there's also a strong correlation between health and income. We don't really understand this, and it's not clear what the direction is. If you think about it, if your health is good, you might be able to earn more. And by the same token, if your income is higher, you may be able to afford a better living environment and better medical care. But there's a very strong correlation, except at the very lowest levels. All right, now we're going to look at a two-dimensional graph. And I told you we'd come back to the age and income. And that little gain we saw around age 62. Well, you can see it very pronounced here for lower incomes, and it disappears for higher incomes. And as you work up the income scale, you can see that the dip becomes, or the rise becomes less and less pronounced. So we would hypothesize here that this is a result of Medicare kicking in at age between 60 and 65. And there's a boost in general health, reported health, especially for people with lower incomes. So that makes some kind of sense. Of course, it doesn't prove the hypothesis, but it definitely illustrates it. And we wouldn't have seen that without looking at a three-dimensional plot that combines the effect of both income and age. All right, now we look at the probability of being healthy, being good or better health, considering your education. And this goes right on the scale of education. College graduates have the highest, best health. Some college is slightly worse, high school is slightly worse, etc. So we don't thoroughly understand this relationship, but there is clearly a relationship here. And between physical activity and health, there's a very strong relationship. Now let's take a look at a little study here. What's the healthiest state? This illustrates some points that I'd like to go over. So if we just ask what's the healthiest state, we see on the left Colorado, Massachusetts, DC, and Minnesota come up as the healthiest states, the states where people reported where the most people reported good or better health. And Puerto Rico, Arkansas, West Virginia, Kentucky, Mississippi on the right side. So that seems reasonable, but we ask ourselves, is this, we know that different states have different age populations and also have different levels of incomes. And we know that both age and income affect health. So what happens if we control for age and income? And this is one of the powerful facilities of the probability space module in Causality Toolkit is you can control for any variables. Algorithmically, you can control different variables. So here we control for age and income, and the results change somewhat. Colorado is no longer at the top. Vermont moved up to the first place. Maine moved up to the third place, and Hawaii. And then on the bottom, Puerto Rico moved up about 10 spots. And Kentucky, West Virginia, Arkansas remain close to the bottom. So we can say that even when you control for age and income, there's still a significant difference between the health of different states. So what do we attribute that to? Not sure. What about physical activity? The amount of physical activity between people in different states. Is there a significant difference there? And if we look, we see Puerto Rico, Arkansas, Kentucky, and Mississippi have the least physical activity, whereas Utah, Colorado, BC, Oregon, and Massachusetts have the highest. So that seems like that could be a causal factor. So we can control for that and see the difference there. But we only have the opportunity to very lightly skim this subject in this presentation. So I'm going to move on. We're going to take a look at a curious relationship here. This is income conditioned on height. Why there's a relationship between height and income? We can come up with a few hypotheses, but it's a bit mysterious as well. So the first hypothesis, which was a very obvious one, is, oh, this is really just a proxy for gender, right? Males are taller than females, so this can be explained by gender. But when we control for gender, we still see there's a definite trend here. It chops off a little bit at the top above 6'3", and it's a little steeper at the bottom. But that doesn't explain. This tells us that the gender doesn't explain this height to income relationship. And in fact, we've tried conditioning on every set of attributes, and we cannot break that relationship between height and income. It's true for males, it's true for females, it's true for both together, and it's true when we condition on any other set of variables that are in this data set. So it could mean that there are variables outside of this data set that are causing it, or it could be that there's an actual impact of height. So two hypotheses come to mind. One is that bigger people can get more physical work done, but that doesn't go away when I condition on education. And so college educated versus non-college educated, this trend doesn't go away. Another hypothesis is that it's a preference for taller people, and that one we have no way of rejecting, but hard to understand this particular relationship. All right, so as we look at these combinations of variables, we notice it's very hard to separate out causes from correlations and what causes it. So if we run our causal discovery algorithms, these actually attempt to separate out, to winnow out the correlation from the causality and represent the causal model. So we take a simple model with just 4 variables: income, height, weight, and general health. And we get mostly intuitive results. Height influences weight, weight negatively influences health, income positively influences health, and income positively influences height. Now we don't understand that one. We put a big question mark next to that particular link. Now, also note about the links here. The strength of the link implies the strength of the causal effect after removing all the correlative information. So these are actually true causal strengths, assuming that this model is correct. If we change the model, we'll get different strengths because we use the model to sort out the correlation from non-correlation, correlation from causality. Moving on, what happens if we look at more variables? Does it still make some kind of sense? Well, here we added 3 more variables. And if you look at some of the stronger links, gender affects height, no doubt. Height affects weight, no doubt. Age decreases weight, but yet weight still decreases general health. So as you age, your weight naturally goes down, which should be good for general health, but the strength of the age link overrides the loss of weight in terms of general health. Interesting. It tells me here that income affects education quite strongly. That's a little hard to understand. I would have expected it to be the other way around. So we put a question mark there. And education affects physical activity. Income positively affects physical activity. And see this double-headed arrow between health, general health, and physical activity. That means we can't quite determine the direction of that effect. And if you think about it, there's 2 ways that effect could go. Greater physical activity yields greater health, or if you're feeling better, you're likely to engage in more physical activity. There may actually be a cyclic relationship here, or a loop in the causal model. But we represent that with a 2-headed arrow saying we're really not sure which direction that causality goes. And as we increase the number of variables, things get a little more interesting and also a little more blurry. So we maintain the links between gender to height to weight, but now we added BMI here. And when we add BMI, weight no longer has an effect on general health. The effect is through BMI. But notice that BMI and weight have a double-headed arrow. We can't determine the direction there. We intuitively know that weight causes BMI because it's a direct calculation of weight and height. But the system doesn't know that, and there's no noise in the calculation. It's a direct numeric calculation. So there's no signal in there that tells us directionality. Same, we have a double-headed arrow between general health and education. Not quite sure how to interpret that. We had a reversal of the arrow between income and education. Now it's pointing from education to income. So as you add more variables, there are different correlations to resolve, and you can get different answers. And sometimes adding a variable will clarify a anomalous result that you see with fewer variables. I won't go into all of these, but most of them make some kind of sense. Being a veteran, for example, there's an age relationship. There's a gender relationship. Most veterans are male. There's a smoking relationship. But anyhow, many studies can be done based on this information. So I'm going to go through one more point and then we'll end. So here we take 5 variables and we look at the causal relationships, and we note that they all make sense except income to education. We expect it to be the other way around. Being more educated would give you more income, especially when you consider that income is present and education is historic, right? I may have gotten my education 30 years ago, so how can my current income affect my education? So we hypothesized that that arrow is wrong and should be the other way around. So our causal toolkit gives you the ability to edit these models on the fly. And so we reverse the arrow from education to income. And we retest the model. That's another capability of the toolkit, is to test the model to see how parsimonious all of the interactions between variables are with the model. And so for this first model, we got a 94.4% score, which is very good, saying that all the pieces fit together. When we reversed it to what we think is more reasonable, we ended up with a 67%. So going back to what's more intuitive doesn't necessarily give you a better model. Keep in mind that this finally did reverse when we added in a lot more variables. So there are hidden variables that we're not observing in this particular model that are making the link appear backward. So that's it. That gives you a quick overview of how to apply the toolkit both statistically and causally to real world data. Shows that there is some power to the detection of the relationships, both in terms of what elements are related and what the direction of those relationships are. So we're very pleased with that. And there's a lot more to be done, but we believe that our causality toolkit is not just a causal algorithm analytics package, but it is really a package for the analysis of any complex data set. Whether you're using the causal capabilities or just statistical capabilities, it provides a very powerful facility. I want to thank you all for your time and attention, and I hope this shed a little bit more light on what can be done with the causality toolkit than you can get through a series of slides. And it is available, version 1 is available on HPCC. The current version 2 toolkit is available from Python and will be available soon on HPCC 3CL. Again, thank you and have a good day.